Yes, students, welcome back to the lecture series on design of RCC structures and sleeve structures. Subject code 17CV72. We are in module 1, that is design of RCC structures, with a lecture number on 9th, presented by Girish Chadgeri. In previous class, we have studied about the design of retaining wall. We studied about kinds of retaining walls when they have used. In that, we have selected a T-shaped retaining wall. We have designed it. We found its components. Before designing, we checked its stability. Then we designed individual component. Just to have a glance over this retaining wall, we can see here a retaining wall was designed where three components were there. One is stem, heel slab, and toe slab. As we did, the stem was designed for the horizontal pressure of the earth provided on backfill there. So pH was found, that is horizontal pressure was found, which a height of. This is a load which is applied over the stem, and maximum bending moment we get it at the toe here. So we have designed the stem for the maximum moment found at bottom of the stem. Where we found the pH value and horizontal pressure, that is nothing but it is in a triangle shape. So area of triangle has been converted into the horizontal pressure. Then the 1/3 of the length will be the pressure into the lever arm. Will get the moment at the bottom, and we found the thickness of stem at that moment. Then we, if once the depth was found safe, then we provided the reinforcement for the calculated movement by using SP16 table 2. Then we designed the second component, that is heel slab. We can see in the diagram heel slab. Before going that instability is only we have found the uplift pressure below the slabs, that is at toe it is maximum, at heel it was less. But we can see from the diagram the backfill will be more in the above the heel slab. So the heel slab, the backfill load plus the concrete thickness of heel slab will act in the downwards, while the uplift pressure will be in the upward, which is less to the downward force. So the heel slab is designed for the downward force. So that's what the reinforcement is given at the top of the slab of the heel slab. And also we have found the shear, and we found it after finding the checking the depth and providing the steel found safe, that is 2V is greater than 2C is greater than 2B. We have continued that. Similarly, we have designed the toe slab. Toe slab also we can see the depth of filling at the rear side is very less. So the toe slab is designed for the uplift pressure at the bottom side. So we can see the reinforcement red color shown here. There the reinforcement is given, designed for toe slab will be in the bottom of slab, and the thickness will be found safe. And this is what the red color I have shown, that the reinforcement provided as per the decision required for the stem, heel, and toe. While the remaining the white color, we can see the reinforcement provided, that is nothing but a minimum reinforcement provided to hold the reinforcement in the position, as well as the minimum reinforcement required at that junction will be provided. And at the rear side of the retaining wall, which is exposed to the sunlight, where we are designing this reinforcement, which is shown in the red white color, shows that the temperature reinforcement will be given on the face, where the concrete should not be shrinking. All the cracks over the concrete should be avoided. That's what reinforcement will be provided for the temperature reinforcement, which will be a minimum steel only. So that is provided on the other face of the retaining wall. So these were a component we have designed. And as I told in the earlier class, types also we found to know in the retaining wall, and that types depending upon the depth we are going to select which kind of retaining wall is provided. If the depth is less than 3 meters, that is a backfill behind the wall is less than 3 meters, definitely we go for the reinforcement, the L shape or T-shaped retaining wall. That L shape, inverted or C vertical. The L-shaped retaining wall be provided when the depth of the filling below the wall is less than 3 meters. When the height of the backfill is more than 3 meters and less than 6 meters, then we design the T-shaped retaining wall, what we have designed in the previous class. Once the depth increases by 6 meters, when it goes beyond that 6 meters, the same T-shaped retaining wall can be written, but what happens, due to the more backfill, the thickness of stem also increases as the pressure increases in the horizontal directions. In the same fashion, the hill slab, what we designing for the will be more, backfill will be more. If 7 meter is 6 meter, more than 6 meters backfill is there, then the thickness of the slab also get increased as per the requirement of the movement. That's what to, and the retaining wall becomes uneconomical. So how to make it economical? How to make it easier way instead to avoid a huge concrete or huge steel? That's what another retaining wall like counterfort, better step, that kind of retaining wall is adopted. So when the depth increases more than 6 meters and beyond, we start to design a counterfort retaining wall. What is this counterfort retaining wall? You can see here a small diagram has been done here. This is also a same T-shaped retaining wall. Only the thing is that at certain distances, we are going to provide. At certain distances, we are going to provide the uh, slant triangle type connected will be between the stem top and the heel slab. We can see this is a T-shaped retaining wall. Let us take it. For this, how will be the plan will be given? We can see the plan for this will be like this. In the plan, we can see like this. Is it visible, guys? You are looking at it? Yes? Students, you are hearing or not? We can see here, when we take a plan of this retaining wall, I can say this as a retaining. Initially, I will take it as a retaining wall. We can see here how we have drawn this. This retaining wall be in this fashion. So this I can take a section like this, that it will be continued for a long period. So I can see this is retaining wall. This portion is toe slab. This portion is heel slab, and this small thickness is stem. This we can see in the section. This is so what, how we can say how we are going to draw counterforts. Counterforts means I am going to take one of the like this triangle shape length, height, and it will be taken in this fashion. So this is one component I have taken, and this component to be shown will be in this fashion. At certain interval, I am going to draw like this. A concrete structure will be built in this fashion. At certain regular intervals, about 3 meters from center to center, I am going to take like this. So when I draw counterforts like this, I can see this part. Even though if I can take like this still more, I can see this. These are like counters. We can see these counters in banks. Banks, when employees will sit in between them, a small counter is made so that a payment will be done or they file maintaining. This is their area to work. Similarly, in this fashion, the counters are provided at regular interval. These counters are like this in this form. It is designed from top of the stem to edge of heel will be drawn, and it will be in a triangle shape. You can see this is in triangle shape, and for this a small thickness will be given in this fashion towards 1 meter. It is all along this 1 meter we are running. It will be like this. So this is counterfort, I say. E counterfort will be designed in this one. This small thickness, about something 300 or 400 thickness of wall will be given. This will be provided at regular interval of 3 meters or 4 meters like this, so that this acts as a counterfort. What happens if this acts as a counterfort? What is the advantage here? When the height increases more than 6 meters, when the height of backfill is more than 6 meters or is 7 meters, something 8 meters, since this counterfort is connected with the stem and the heel, the pressure what is there in the soil acts in this fashion. This will push, and we can see this will push like this. This will push like this for the stem. Same fashion at hill slab also it pushes like this. Soil will be pushing in this fashion. So what happens when we take only a stem here, stem part, this is connected with the one counterfort on this side, other counterfort on this side throughout the height, and bottom also is it fixed with the hill slab. So a small counterframe, when it acts like this, we can see if you take a section of only the stem I am telling, the stem will be like this. This is the stem height. And the counterforts are provided at some regular intervals. This is one counterfort, this is other counterfort. So counterforts, and at bottom it will be stopped here, and this here at this level we got heel slab. So this is height of counterfort, means stem. These are two counterforts in between this section I am taking. So this will be height of. What happens? Entire area is fixed with counterforts on either sides. Bottom is it is fixed with hill slab. So only one end is free. So how it will be designed? Can anybody having idea here? Students? Are you hearing me? Can anybody tell? Hello? Anybody?
Yes, sir.
How you, yes, tell me how you are going to design this stem now. This is a stem which is connected with one counterfort, other counterfort. We can show in section like this, connected here, other is connected. At the bottom it is connected with the heel slab like this here, bottom also it is connected. So three side it is connected, only one side it is free. So then how we are going to design this stem? Any idea? I think we can use the table number 26 from IS 456 2000. Anybody having remembering the table here? Table number 26 from IS 456 2000. Anybody having idea? For what the table belongs to? Anybody? Anybody is having idea about that table number 26? Jayashree, any idea? This acts as a slab now. This small component, this part acts as a slab. We can see, since this is connected with the supports at both ends, this will have a negative reinforcement at these edges. These edges will have a negative reinforcement. I can show in bars. And since it is connected with the bottom also, this part will have a negative reinforcement. Only this part, center parts will have a positive reinforcement. So this will be designed as a slab here. So the movement to positive movement and negative movement will be WL square by 12 and WL square by 16. WL square by 16 will be the negative reinforcement at the edges. WL square by 12 is the positive movement at the midspan. So here there is no support. So at this we can see in the midspan area, the movement will be WL square by 12. And at edges where the movement is less, which is in negative direction, that will have a load of WL square by 16. So what is W here? The dead load plus live load acting on the slab. Here we can see the dead load will be the soil pressure which is in the horizontal directions. That itself is taken as W here, which is acting at the downward will be maximum. As we can see, the load of the pressure of the, we can see the pressure of soil will be in this fashion here. So pressure will be maximum at the bottom itself. We can see pressure will be maximum at the bottom. So At this point, W will be taken considered, that is nothing but a PH, horizontal force. The PH itself will be the W here, and L is the span between the counter force, that is distance between the slab width. W square by 12 will be the movement at midspan here, and W square by 16 will be the movement at edge. This is how we are going to design the stem. Since it is a slab type designed, a small component will be taken. The thickness of the stem get reduced. It will be in a straight with the same thickness throughout without having any taper dimensions like we did in a retaining wall. In the similar fashion, when we look into the bottom slab, again the hill slab we can see here, the hill slab is also connected with the counter force on either sides with the stem on one side it is free. Again, this bottom hill slab will be also designed as a slab itself with a load of W square by 12 as a mid-span movement, W square by 12 as a W square by 16 as a negative movement at the edges where it is connected with the counter force as well as slab. This is what we can see in the counter force. So heel will be heel slab as well as stem will be designed as a slab here with the W square by 12 movement maximum at midspan, and at end supports where it is connected with other structures, the movement will be W square by 16. Then we are going to design the toe. Toe will be designed as usual here. The pressure what we get in the toe side will be in this fashion. Downward force. This is a downward force. Definitely there is no load over this. So the toe will be designed for the uplift pressure which is maximum at the bottom. While the heel slab, we can see the downward force will be more. So it will be designed for the downward force. So the reinforcement pattern will be same as we did in the cantilever retaining wall. Only the thing we need to calculate the stability first. As usual, we are done in the retaining wall. When the given data will be given, take down the given data, list the given data one by one, then know what should be required, what is requirement, then give the dimensions as per the H value calculated, that is backfill plus the depth of foundation. Once we get the total H value, from that you design the dimensions of retaining wall, that is width of base slab, thickness of base slab, width of stem, thickness of stem at the bottom as well as top. Like this, give all the dimensions, length of hill slab, length of toe slab. All these dimensions will be calculated as per the proportionals given by the height of the backfill. Then once the height is proportional dimensions are given for the counterfort retaining wall, check it for stability. That is the moment of resistance against the moment of overturning. What we did in the retaining wall, that is 3 steps. First check is for overturn. Second one, check is for sliding. Then third one, check for the uplift pressure, which should be less than the SBC of the given thing. So that will be done as we did in the retaining wall. We will check the stability. Then we check for water, check for slide, check for the uplift pressure. And all these will be well within the required one, and it is safe. Then we are going to design the component individually. That is, the stem component will be designed individually, the heel slab, the toe slab. Then we are going to design an extra component, that is counterfort. So counterfort again subjected to the slab here, this soil, and which will be in horizontal direction. Depending upon the force, we are going to provide the reinforcement in both the directions. So this is a glance I have given. Let us go with the things here clearly. What is counterfort? We can see here. When the height of retaining wall exceeds about 6 meters, the thickness of stem and heel slab works out to be sufficiently large, and the design becomes uneconomical. In such cases, the counterforts are having a trapezoidal sections, that is triangle, which is fixed as base slab as well as for the stem, and they are provided at the interval of 1.5 to 3 meters. These supports heel slab as well as vertical stem. Hence, the design principle for the different components of the walls are discussed as under. So I have shown here the counterforce here. This is a stem part, heel slab, toe slab. This is a backfill height, what is given H1. Then the depth of foundation. So total height will be H1 plus depth of foundation. We get the total height of backfill. This H will be the height of stem after deducting the slab thickness. We can see this in the same in the plan. This is a toe. This is heel. This is stem. These horizontal given at regular interval are counter force. So this acts as a counter for the person sitting there. Then, as I discussed from the AutoCAD drawing, the stem acts as a continuous slab spanning longitudinally over the counter force. So horizontal active pressure acts as a load on the slab. Since earth pressure varies over the height of the stem, that is from top to bottom, the pressure varies. At the top it will be 0, at the bottom it will be maximum. So the slab deflects away from the earth face. Hence main steel is provided at the outer face of the stem and the inner face of the supporting counterforce. The bending moment in the stem is maximum at the base and reduced towards the top. Thickness of wall is kept constant and the only area of steel will be reduced. So let us assume the clear distance between the counterforce. As I told, 3 meter will be given between the counterforce from center to center, assuming the thickness of some counterforce. Deducting that, we get the distance between the counterforce. And let P be the intensity of pressure that is applied in between the counterforce. So the maximum bending moment will be negative at the inner face of at the edges. It is PL square by 12. This is not PL2, it is PL square. Super skipped. So maximum positive movement will be PL square by 16 at the midspan. And PL square by 12 will be the maximum negative moment at the edges. So depending upon the moment, as I told, the pressure of the stem will be maximum at the bottom of the stem. So there we get PL square by 12 as a maximum moment. P stands for intensity of pressure by the soil. L stands between the distance between the counterforce, between the stem what we have provided. For that, the depth is checked, and for the given depth, the shear is checked. Once it is found safe, we are going to provide the reinforcement at for that moment at the near the junction where both ends connected. This is regarding the stem design. The same design as I told in his slab will be the same design, PL square by 12 and PL square by 12. And coming to toe slab as we know already, for uplift pressure it will be designed the same thing what we have done. Next we are going to design the counterforce. So counterforce are sloping. We can see here counterforce are this one. This is a counterfort, and this is subjected to the horizontal pressure like a triangle shown here. For this show, we are going to design. So let us consider a small problem so that we will come to know the components one by one. First today, let us calculate the component wise the dimensions of the counterfort. So take a problem here. RCC retaining wall with a counterforce is required to support earth to a height of 7 meters above the ground level. The backfill is 7 meters above the ground level. The top surface of the backfill is horizontal. When the trial pit was taken at the site, indicates that SPC of soil is 220 kilonewton per meter square. And this SPC is taken at the height of 1.2 meter below the ground level. That means the depth of foundation is given in the question itself. That is 1.25 meter is the depth of foundation given. The weight of the earth is 18 kilonewton per meter cube. And the angle of repose, that is 30 degree. That is the internal friction between the soil properties will be 30 degree. The coefficient of friction between the concrete and the soil is given as 0.58, that is mu value. Here we are going to use M20 grade concrete and Fe415 steel. We need to design all the components of retaining wall connected with this. So as I told, the first step, Whenever a problem is given, kindly write down the given data here. So you can see the given data: FCK20, F5415, that is steel. The bearing capacity soil is given as 220 kilonewton meter square. The height above ground level is 7 meters. The depth below the foundation is 1.25 meters. Hence, the total height will be 7 plus 1.25. 8.25 meter is the capital height. That is depth of foundation, total depth of the backfill. The density of soil is given as 18. And the angle of repose, that is friction between the internal friction between the soil property is 30 degree. Then the coefficient of friction between the concrete and the soil is 0.58, that is mu. So this is a given data what we have got from this above problem. Next, let us assign the dimensions for the retaining wall. So height of the wall, h, we know it is 7 plus 1.25, that is 8.25. Base width, you can see it is 0.6 to 0.7. The 0.6 of h will be 4.95 and 0.7 of h will be 5.78. So in between this, the depth should be provided. Width of the base width should be given. So we are assuming the base width as 5.5. Then the toe projection, that is 4.5. 5.5 is the, we assume width divided by 4, that is 3 to 4, it should be the toe projection. So when we divide it as a 4 maximum, we get 1.2 meter as the toe projection beyond the stem. So assume the thickness of vertical wall, that is stem, as 250 mm. That is throughout the height of vertical wall will be same, 250. The thickness of base slab is assumed to be 450 mm. Then we need to assume the distance, calculate the distance between the counterforts. The formula to find the distance between the counterforts will be L equals to 3.5 bracket of h by density. H is total height, that is 8.25. So 3.5 bracket of 8.25 divided by 18 density into raised to 0.25. The length clear span between the counterforts will be 2.88. We are assuming the thickness of the counterfort as 400 mm. So before going that, the spacing between the counterforts will be 2.88 plus 0.25, that is thickness of stem. We get 3.3. Let us say we are providing the counterforts at a distance of 3 meters from center to center. Then the width of counterfort is 400. So the clear spacing between the counterforts will be capital L, that is 3 meter minus of 0.4. It will be 2.6 meters, the clear spacing between the counterforts. So these are the dimensions we have calculated in the today's class from the given data. So we can draw the diagram here. We can see H1 7 meters, that is given backfill. 1.25 depth of foundation is given already. From these two height, we got total height as 8.25. Once we got the total height, calculated the base width, that is 0.6 to 0.7 will be the height, will be the base width. So we're assuming the base width of is 5.5 meters. Then we calculated the 1.2 meter, that is projection of the toe here. That is 5.5 divided by something 4. We got 1.2 meter as a toe projection. Once you know the toe width as well as the base width, that is 5.5. Toe width is 1.2. The thickness of stem assumed as 250 throughout the height. Then the length of the base slab, that is width of the base slab, we can say heel slab, that will be 5.5 minus of 1.2 minus of 0.25, we get 4.05 as the width of heel slab. So the height of the backfill will be total 8.25 minus of thickness of slab, that is 0.45. We're assuming the thickness of base slab. So 8.25 minus of 4.5, we got the height of backfill for the design of stem will be 7.8 meters. How we got it? 8.5 total height minus of thickness of slab, we are assuming 450. So 8.25 minus 0.45, we get 7.8 as the height of backfill for the stem design. And assuming counterforce at a distance of 3 meters from center to center, calculated as per the formula given. So the counterforce are provided at a distance of 3 meters center to center, and the thickness of counterforce is taken as 400 mm. So this is the dimensions calculated here. And in tomorrow's class, we start with the stability check as well as design. Before going that, in till yesterday's class, we had done a cantilever retaining wall. Assignment 1 was given, that is of combined footing, slab type. I think nobody has submitted it. Saturday was the last day to submit, so another one day I will give. Kindly submit your assignments through Microsoft Team only. There is option to submit your assignments. I will tell you how to submit the assignment. You can go to your Teams, go to the 7-sum class. At the upside file, we get files, notes, all something. In that files, open it. We get new, upload, synchronize, something like this. There you upload your assignments, and for that you will get a internal marks. So in today's class, we are giving another assignment 2 for the cantilever retaining wall, which is cleared in the yesterday class. That is question number 2 from January 2019. I have taken a question here. So write down this question, and this notes will be sent to your group here. Actually, I have not sent any notes for you people, so I am giving the notes of the retaining wall as well as the combined footing in one slot only. Full entire design of combined footing will be in one file, and the entire design of counterforce will be in another file. So both the files will be uploaded in your Microsoft Team today itself. By another 1 hour, I am going to upload both the notes. Utilize them and write down the assignment and submit it by. If you want to submit both assignments, submit it by next Saturday. If you want to submit first assignment, you can submit it by tomorrow. Don't take it as an excuse, because the internal marks will be based on your submission of assignment also. Clear? So in today's class, coming over to the Bloom's Taxonomy, CO1, that is course outcome 1, PO1, that is we are studying only theory purpose today, and the level of will be only 1 and 2, that is recalling the fact of basic concept. Whatever learned in the previous class, that basic is recalled and we have designed. So only remembering we have done, and part of L2 will be done, that is the concept ADAS will be given how to do design the components. That's what in today's class, level 1 and level 2 you have learned from course outcome 1 and program outcome 1. This is what you have learned in the today's class. Hope you found it good. In the next class, we are going to design the stabilization of the counterfort. Then we are going to design the further things. Clear?
Yes, sir. Yes, sir.